And I'd like to introduce to you Aniketh Girish, a PhD student at the IMDEA Networks Institute in Madrid. And a couple of words about Aniketh. He's focused on hybrid black box testing, covert privacy risks in smart home and mobile systems, and regulatory compliance. And he's been publishing in top venues and journals. His work, very noteworthy, actually exposed tracking practices that led companies like Google, Apple, and Philips to change their policies and designs, and it even influenced EU privacy enforcements. And needless to say, such excellent work also receives a lot of international coverage by media. And very much looking forward to your presentation, Covert Web-to-App Tracking via localhost on Android. Welcome, Aniketh.
Thank you for the introduction, and I'll be presenting my work on discovering a novel side channel, one that bridges both sandbox environments like the web and app on Android through the localhost interface. This work was done in collaboration with folks from KU Leuven and Radboud University. So to start off with, both mobile and web platforms are designed to enforce strict contextual isolation. On Android, this takes the form of UID-based sandboxing, where each app runs on its own process space. Apps cannot directly access each other's data or resources without going through the platform-mediated APIs and permissions. On the web, policies like same origin or cross-origin and many others restrict how one website can interact with another. Communication across these contexts, say from the browser and to the app, requires explicit user intent. This contextual isolation is fundamental to users' privacy. But what if there's a way to bypass these boundaries and a narrow but shared interface exists between apps and web, the localhost interface? So let's unpack how this localhost path works in practice. On most platforms, apps can freely bind it to it, and also browsers can allow JavaScript to connect to it. This exists for legitimate reasons like developer dashboards, local testing frameworks, or peer-to-peer fallback connections. But what's interesting is what the setup enables. Any app can expose a service, and any website can silently reach it across context boundaries. This is the unprotected case of platform design, and the real question is, does anyone actually use it in this way? To answer that, we first need to understand why this channel often flies under the radar despite being openly accessible. That's because it operates entirely outside the scope of traditional platform defenses. It doesn't trigger permission prompts, it's not blocked by browser security models, it's unaffected by incognito mode, cookie deletion, and even VPNs usually ignore loopback traffic since it never leaves the device. So what we end up with is a side channel, one that quietly bypasses sandboxing, permissions, and user expectations entirely. What we are seeing here is a systemic breakdown of expected defenses by the use of localhost interface. So this brings us back to the critical question I mentioned earlier. Does anyone use this localhost interface to reach a mobile app, and in doing so bypass both the web and app isolation models? It turns out the answer is yes, and that's exactly what we found. We discovered for the first time the side channel is actively used in the wild by Meta and Yandex, a Russian giant, affecting billions of users globally. So now let's take a look at this practice a bit more closer, and brace yourself because we are going to get into the nitty-gritty technical details of how this works. So in the case of Meta, we saw the local host-based mechanism being used together with their pixel infrastructure. So let me walk through the full sequence of the steps, highlighting how this cross-context channel operates end-to-end. So Meta apps, particularly Facebook and Instagram, quietly runs in the background on Android, even when you're not actively using them. They open up specific localhost ports, both TCP and UDP, and listen for incoming traffic from the browser. Now here's where the traffic kicks in. Let's say the user opens their favorite browser and visits a website. If the site has metapixel embedded, it executes a JavaScript in the browser context. This JavaScript knows to probe the localhost ports, attempting to establish a connection with the meta apps. At this point, the pixel script creates a first-party cookie called FBP cookie. So according to the Meta's documentation, this is a unique ID for the user's browser session on the domain. It's supposed to be scoped to the browser and the website domain, not visible to the native apps. But that boundary gets violated in the next step. To transfer FBP cookie to the browser, from the browser to the native apps, the Meta uses a clever trick involving WebRTC, a technology originally designed for real-time audio and video communication. As part of setting up a WebRTC connection, browser sends what's called a stun request, lightweight messages that helps determine the device's public IP address and connectivity path. Normally, these messages follow a strict format conforming to an RFC and aren't meant to carry user data. But in our case, Meta modifies this process. Instead of using the Meta's API, WebRTC APIs as intended, they manually alter the configuration data called the Session Description Protocol (SDP) to embed the FPP cookie value inside the stun request. This technique is often referred to as SDP munging, where WebRTC standards expect SDP offers to be passed unchanged, but some browsers didn't enforce this, enabling such kind of workarounds. This lets the native app read the cookie data directly, circumventing any browser sandbox or cookie scope restrictions. Once the app receives the FBP cookie, it relays it to Meta's servers through their regular GraphQL API calls. And this process bridges the anonymous web sessions to the user's logged-in identity in the app. But WebRTC wasn't the only way they connected both browsers and the app. Of course, over several months, Meta's use of localhost changed in several key ways. Let's take a step back and look at how this behavior evolved across time. Back in September 2024, we first saw the simple HTTP request on one particular port. By November, they shifted to WebSocket traffic, still using the same port. The same month, they started rolling out this WebRTC stun request method on a range of ports where the FBP cookie was injected to the SDP offer using SDP munging. And by May 2025, things had started to change again, and Meta moved to WebRTC turn traffic on a new range of ports. So over time, they cycled through different protocols, port ranges, but the goal remained the same: to link browser sessions with native app user logins and IDs via localhost. Although both Meta and Yandex deployed mechanisms that used the localhost interface for cross-context tracking, we found no public-facing documentation mentioning these practices, not in SDK guides, developer references, or in change logs. But what we did uncover, however, was a series of developer forum posts on Meta's official platform dating back to September 2024, in which third-party developers reported some weird behavior. Specifically, Meta Pixel JavaScript was issuing requests to localhost when embedded in Android web views. These reports were not isolated. Multiple developers expressed concerns and confusions, and there was no official response from Meta. One developer, speaking of the broader frustration, wrote, "No acknowledgement has come from Meta at all on this, and my support request with them got a generic response and then got ignored." So next, let's look at a different implementation of the same idea, but this time by Yandex. While the core mechanism is still based on the local host communication, interestingly, Yandex differs in its approach. Compared to the Meta's case, it's the browser that sends the data out of the server, not the app. And the app just acts like a middleman bridging native IDs to the web. Let's, again, take a look at it from a bit more closer. So here's how the full loop works. Many Yandex apps include the Yandex Metrica SDK, which is developed by Yandex itself. So yeah, SDKs are essentially a plugin code bundles that help developers add features like analytics, right? And Yandex Metrica SDK runs in the background and listens on a specific localhost ports. When user visits a site with the Yandex Metrica script, the script first fetches obfuscated parameters from the Yandex servers, and then these parameters are then sent back to the local Yandex app. The app receives these requests and replies with encrypted device identifiers such as the device IDs and Google advertising ID. And finally, the script is then forwards this information back to the Yandex servers. Apart from this, we also found a couple of things particularly interesting with Yandex's case. First, they used a domain that resolved to the loopback address. Yandex's approach relied both on HTTP request to the loopback address and the HTTPS request to yandexmetrica.com, a domain that resolved to the same loopback address. In both cases, the browser send obfuscated parameters to the local ports, and then this dual design helps conceal the true destination of the data, making it look like a standard web analytics traffic while actually reaching a native app on the same device. Second interesting point was that Yandex app did not immediately begin listening on the localhost ports. Instead, they first contacted a Yandex domain endpoint to fetch a configuration. This included a list of localhost ports to listen to and a parameter called first delay seconds, which was roughly set to 3 days. Once the delay runs out, the app silently starts listening on these ports, enabling localhost-based tracking. And this is significant for two reasons. First, it likely serves as a stealth tactic, delaying socket activation until long after app installs, making detection much harder. And second, it's clearly coordinated. Yandex controls where the socket opens and which port through the remote config. And Yandex's use of localhost communication channel is not new. It dates back 8 years. In February 2017 is when we observed the first HTTP traffic on these specific ports. And just few months later in May 2018, they introduced the encrypted HTTPS traffic over 2 different ports. Beyond identity bridging, these localhost mechanisms introduce a secondary privacy risk, the leakage of browsing history to the third-party apps. Specifically, the use of HTTP as implemented by Yandex Metrica and the earlier versions of Meta's channel opens up a privacy risks. HTTP request from the browser includes the origin header, so any unprivileged app listening on the same localhost port could see which website triggers this request. And this means a malicious app could quietly harvest a user's browsing history just by observing these local connections. They allow for re-identification and breaking pseudo-anonymization of data. Our test shows that browsers, including Chrome, Firefox, Edge, were vulnerable to this type of leakage, even when users' browser is in incognito mode. DuckDuckGo was minimally affected due to a few missing Yandex domains in their block list, which they fixed quickly after we disclosed it. Brave wasn't affected. It blocks localhost requests and known trackers by default. While we did not identify any third-party apps outside of Meta and Yandex currently listening on these specific ports, the possibility remains open and the attack surface is now known. So far, everything we have shown is based on real-world evidence from the Android devices. So in our test, we also saw that Android was particularly targeted. But we did not find evidence of similar behavior in iOS. But that said, it's important to clarify that our focus was primarily on Android. So we did not perform equally deep analysis on iOS. Technically, apps can spawn a local host server in iOS. However, iOS differ in some unique ways. iOS imposes much stricter background execution limits and enforces tighter control over process lifecycle. Lastly, the broader concern here goes beyond Android or iOS. Localhost is accessible across a range of platforms, desktop apps, smart TVs, or IoT systems, many of which haven't yet been studied in this context. So while we did not observe this attack on iOS, the underlying design pattern creates a much wider potential for such attack surface. Now let me highlight some of the impact of this findings has had. So to start off with, to understand how widespread this local host behavior really is, we look beyond just the technical feasibility. So according to BuildWith, a web analytics service that tracks third-party technologies across millions of websites, we found that over 11 million sites globally embed Metapixel and more than 1 million uses Yandex Metrica. And these are massive deployment numbers spanning news, e-commerce, governmental, and health sectors. But those numbers alone doesn't reveal when or how the local host channels is actually used. So we conducted our own dynamic tests, crawling the top 100K websites using vantage points in New York and Frankfurt. What we found was interesting. Not only Meta and Yandex were widely embedded, but majority of sites using them initiated localhost probing immediately before any user interaction or consent. As you can see here, in the US, over 78% of Metapixel's sites and over 83% of Yandex Metrica sites made local host requests without waiting for users' permission. In Europe, under stricter regulatory regime, the numbers are still comparable, over 75% and 84% respectively. These results suggest that local host abuse is not only real, it's global, it's widespread, and potentially without meaningful user awareness or control. And as part of our responsible disclosure, we worked with major browser vendors to address the side channel uncovered during our study, and their collaboration was active and constructive throughout. So Chrome was the first to deploy defenses in May this year. They introduced two key mitigations. It blocks specific abused ports used by Meta and Yandex. It disables STP munging of ICE credentials in WebRTC, the very technique used by Metapixel. In parallel, Chrome is also working on local network access LNA restrictions, and this feature is being currently tested on newer versions and serves as an added barrier for local host requests by requiring user permission under certain contexts. Firefox already had protection in place to block STP munging of ICE credentials, and hence only was partially affected by Meta's local host usage. They shipped a port blocking fix in version 139. DuckDuckGo amended their block list to include Yandex domains that we discovered during our research, and Brave, interestingly, was never affected as it required user consent for local host access since 2022. But browser mitigation only goes so far. These are patches, not permanent fixes. Fully addressing this issue means rethinking local host permissions, platform level visibility, and Android's IPC trust models. The response to our finding extended well beyond the research community. Major international outlets like Ars Technica, Sky News, The Washington Post covered the story, helped raising broader public awareness about the new class of tracking. One quote from the Google representative stood out, who stated that both Meta and Yandex were using capabilities present in many browsers in unintended ways that blatantly violates Google's security and privacy principles. After our work went public, both Meta and Yandex provided their statements to Ars Technica reporters. Meta called it a miscommunication with Google's policies and said they paused the feature while they are working to resolve the issue. Yandex also confirmed it was discontinuing the practice, but emphasized that it was complies with data protection standards, suggesting it didn't collect sensitive data and was meant only for personalization. We also engaged with several European data protection and competition authorities across France, Spain, and the UK, and with our findings on platform compliance and local data access practices. Finally, to conclude, our findings suggest that Android's current isolation mechanisms may not fully prevent cross-context communication with localhost. We observe that native apps and websites can exchange information through this local channel without requiring explicit user permission or generating visible signals. This challenges common platform assumptions about how app and web boundaries are enforced. Importantly, we document the real-world deployments by Meta and Yandex, where identifiers such as the advertising ID and login tokens were linked with web cookies. This demonstrates that this technique was not just merely hypothetical. This observation highlights the need to re-evaluate the trust boundaries on mobile platforms. In particular, the assumption that no permission means no access does not hold anymore when local network communication is used, local host communication is used between apps and browsers. We also found that existing defenses such as the sandbox, incognito mode, permission prompts did not offer any effective safeguard in this context. This is in part because these defenses are largely browser-centric, and going forward, addressing this issue may require a platform-centric solution. This includes stronger sandboxing around localhost access, improved network permissioning that accounts for local interfaces, and better auditing of app-to-web interactions. And thank you for listening, and I'm happy to take any questions now.
First of all, thank you for the findings, because I really shocked when I discovered when I actually heard the news. I heard it is like in maybe last year. I don't know, somewhere there. I wonder, like, if you try to discover other kind of similar side channel attacks in map applications, especially on iOS, because using a location services in iOS is really common to overcome the restriction on the background context.
Mm-hmm. So we did, while we were investigating this particular local host channel on Android, we were curious of what's happening in the iOS world as well. So we did look at what's happening there. But as I mentioned during the talk, that the iOS imposes more of a stricter rule on how an app can listen on the background. And for that, they require specific entitlements, as you mentioned, like location, audio, or and there are a few others. So for that, the app developers has to like request it from the Apple, and it's more strictly enforced. So we didn't like end up doing a deeper analysis of it, as we were mostly focused on how it was happening, and also like second, there was like evidences from the scripts that Meta or Yandex sent to the mobile world that they were specifically targeting Android, and so we just we just made sure our analysis remained to Android in that context.
Thanks for the answer.
Thank you for the talk. This is really good research. My question is, so what are the remedies here? So do you know, for example, if this behavior violates Play Store policies, would App Store removal have been an option on or protection and review?
It's I think Google representative here should answer that question, but according to Google's Play Store policy, doing something like this is considered harmful. So there is specific sections in the policies that explicitly describes like you should not bridge different identities from different part of the context, and breaking such kind of a context is not subscribed by Google. But yeah.
Just to give you a bit of outline, it's more of a statement than anything. Back in 2022, when we rolled out the local host, it was due to we started noticing some financial sites. We didn't just, I think it was eBay specifically, had local requests coming through, and we took that opportunity to stop that from happening, because it was scanning. I guess it's sort of anti-bot protection from threat matrix.
Mm-hmm.
And what was happening is that every time a user would go to that site, it would start blocking said requests, or show the local host requests come through. And we took the time to say, well, this is not a good thing to do. So we had to take action. That's when we implemented the local post block for eBay, but also other sites as well. There's a lot of financial sites that use local host as a mechanism to check whether you're a bot, basically.
Yep.
And it's not secure. Just a question regarding IP. Is IPv6 involved at all? Like, can the same apps use IPv6 in the same way if they want to avoid like the 127 local host option, but use it rather than say use the IPv6 version to, I guess, snoop on people?
Mm-hmm. So if on my top of my head, I think so. But I can get back to you on it, as we have a follow-up study on it that we did right after this, and we have a publication. We are pending a publication on it. So I would like to go back on it and just get back to you with the right answer.
Yeah, thank you for the amazing talk. Ramdan, I'm curious, do you know what the rationale is for, you mentioned that the kind of protocol that they were using to access localhost was changing over time. Do you know why they might have been changing that?
Not particularly. They kept rolling out different versions of it. I'm just speculating here, but the WebRTC stun request way of doing a localhost tracking was like disclosed to Meta a couple of weeks before the whole public disclosure was done, and a few months later we also saw the WebRTC turn request popping up. So we don't know what was the rationale behind it, but then we saw there's like a variation of how they use different protocols but essentially for the same purpose.
I see. And then could you share more about how you were able to discover these practices being used? Because it sounds very challenging to discover the index one in particular, right?
Mm-hmm. So we, as a research team, has years of experience on Android analysis and mobile privacy analysis. So we have instrumentations of the mobile operating system and also like dynamic instrumentation toolkits that allows you to like monitor apps during runtime in a black box analysis method. And you get like visibility into like how the app's running, and also along with network forensics. So what sort of network traffic flows in and out of the app. So essentially like by looking through each request and figuring out what's happening, and like trying to use Frida, which is again a dynamic instrumentation toolkit, to patch the code, to patch up as the app to see what exactly happens. So that's how we kind of did the experiment.
Cool. Yeah. And then I guess the last one is, do you know, have you reached out to Google about this? Do you know if they have any like plans to add a permission for this for apps or anything like that?
We did reach out to Google. I'm not aware if they are in plans to add a new permission for this, but I could tell you like a couple of years ago, we did find somewhat similar in the local network issue, and they did roll out a local network permission recently. Yeah. But it doesn't consider local host yet. So I think they're aware of it, and what their rollout plan is something that I'm not aware of.
Cool, thank you.
Sorry to bug you again. Since all publicity has occurred behind the site, obviously when you use articles, what's the status right now of localhost and Meta and Yandex? Are they still doing it, or have they?
No, so like we were still exploring this, and a couple of months ago, while we disclosed it, they had stopped the behavior, and until now, as we have been keeping track on whether they have restarted the process, we haven't seen it.
Okay, so stopped.
Yeah,
That's good.
I think so.
Is there any other apps that do this, or is it?
We also looked for it if there was any other apps or third-party scripts or SDKs that are doing this. As you mentioned, like fraud detection SDKs kind of do this but again, I think it's for a legitimate purpose, and also we didn't see there's like a combination of like the web and the mobile world for it happening. We only saw like scripts sending in localhost probes, but essentially I feel like for something like this to work at a large scale, you need like a larger presence on both on the web and in the mobile. So in the case of Meta, it makes sense that they have millions of users of the Meta pixels on the website, and then Facebook with billions of users on the phone. So it makes sense to like have an infrastructure for this. And what's the benefit of a smaller entity to do that? It's still unclear. But there was a couple of examples of third-party scripts doing localhost probing, but we don't know the purpose of it.
Thank you so much for the talk. A couple of questions. One of them is, this technique, it probably also makes sense to check on desktops, right? So it's much easier to listen to localhost. How it happens? Have you ever tried to look for like people who exploited on this?
No. So while we were investigating this particular case, as I mentioned, like we saw that they were particularly targeting Android users according to their scripts. So we targeted just Android for this analysis. But again, the attack surface is open for desktop apps as well.
And have you checked? Does Safari provide any kind of local host permissions? They I know that iOS often out of scope here. Well, do they at least have a permission for that?
On top of my head, I don't think so. But then they have this protection, a stricter protection for mixed content. So HTTP and HTTPS for, so because of that, loopback props fail. But then there are ways to like again connect to the localhost server.
Yeah, and the last, not a question, but maybe an idea for further studies. So on Android, when you use a Facebook pixel inside of your app, Facebook communicates to their apps. So basically, they extract your Facebook user identifier, and report your how you use a third-party app. And there's no way around it, probably. This is still probably an interesting thing to take a look at. On Android, this is a known thing. Maybe they do the same on iOS, for instance. Something that can be, at least in iOS, IPC between different apps is not as easy as it is on Android. And it is interesting to see if they found a way around that.
Yeah, absolutely. Thank you for the suggestion.
Thank you so much.
So thank you for the talk. A bit of a technical question for me. So I was wondering, the WebRTC method you mentioned uses modifying of the stun and turn response from some kind of stun turn server. So I was wondering, since you mentioned that the browsers basically patched this by making that response, I assume, immutable or something like that, wouldn't be possible in that case to use a malicious stun turn server that does response with what you want, basically, instead of modifying it in the browser? Because if I remember correctly, you can in the web spec like specify your own stun.
Yeah. So yeah, I think absolutely that's feasible as well. Like Meta owned malicious WebRTC stun or turn server could actually then collect the information rather than stitching it with the pattern. But yeah, that totally makes sense.
Okay, thank you.
Non-technical question here, and something I might have missed. For a regular user, if they are blocking the pixel, does that prevent this from even happening in the first place?
Yeah.
Okay, so it depends on the pixel actually being activated without an ad blocker.
Yeah. So basically, if the ad blocker that you have blocks all of these scripts, it's that's blocked in the first place. Yeah.
Okay, thank you.
Right.
All right.
Thank you, Aniketh.
So much.
This was very, very interesting.